Buckling is an important failure criterion to test for, even if a static stress study determines that your models won't yield. This is because buckling failure is not necessarily a function of stress, but one of geometric instability, meaning that it can occur at low stress values, or when you least expect it. The good news is that if you know what you're looking for, predicting buckling potential is easy. So let's start there. To figure out whether or not you should investigate buckling potential, check two things. Is the part in compression? And if so, is it slender? Compression versus tension is straightforward, but defining whether or not something is slender is up to debate. I've heard rules like if the length is 20 or 10 times that of the width, but why risk it? Do like you should when dealing with significant others, always err on the safe side. To help demonstrate the effects of slenderness, let's look at a simple example using a T-beam. Here I have two versions, with the same cross-sectional area, material, load, and fixture, however the first is significantly shorter than the other. Using the compare workspace, we can see the buckling results side by side, and what's important to note is the buckling load factor, which brings me to interpreting results. For the short case, this factor is at 6.35, and for the long case it's at 1.6. So what does that mean? Well, it means that in order to get this to buckle, the load in the setup would need to be multiplied more than 6 times for the short case and almost 2 times in the long version. Considering the original value of 1.4 ksi, this translates to a 3-ton difference between these two cases. So yes, the longer this beam gets, the more prone it is to failing due to buckling. A quick side note, if the buckling load factor comes back negative, it means it's actually in tension, and the load would need to be reversed to cause a buckling failure. This can happen more often than you think, because truss designs will often put some members in tension and others in compression. It's also worth noting that you can calculate for many different buckling modes, adjustable in the study settings, but you're typically only interested in the first, which is the lowest. In the last example I'm changing to, again using the same load magnitude, you can see the first buckling mode is now less than 1. This means that this beam is expected to buckle at about 70% of the expected load. But what gives? Why is this one so much different? Well, that brings me to my third point. Perfectly normal. As I rotate the view, the difference will be apparent shortly. The load in the failing case isn't being applied perfectly normal. It's being applied at an angle, which for this T-beam introduces far too much instability. That said, it's important to consider adding small defects to the loads you're using in these studies because it brings to light instabilities otherwise unpronounced by perfectly normal, perfectly distributed loads. This water tower suffers a similar fate, of very nearly failing under a similar load that was placed off-center and using a limit target. Finally, in this staircase example, I wanted to show you a way to directly calculate the load required to force a buckling failure. As I go to access the multitude of buckling modes, you might notice the multipliers here are anywhere from 1,000 to 13,000. The reason for these massive numbers is because the load, defined in this case, was a single pound. By defining it in this manner, the results now directly reflect the load that causes buckling failure. I hope that in watching this, you know when to use a buckling study and when to be concerned at the results. That's all for today. Thanks for watching.